Welcome to Tech Bytes and News, your daily roundup of articles featured in Hacker News. Today, we're diving deep into a fascinating case study, a mysterious out-of-memory error in a Rust service. It's a real nail-biter.
Oh, I love a good debugging story, especially one involving Rust, which is known for its memory safety. What made this one so unusual?
Exactly. This engine gateway service, a relatively small component handling client connections, was running smoothly for months, using less than 50 megabytes of memory. Then, bam, an OOM killer strikes. The Kubernetes pod crashed, but the monitoring showed nothing unusual leading up to the crash. No memory leaks, no spikes, just a sudden death.
So the monitoring was completely misleading? That's terrifying. What did they do?
They checked everything. CPU, network, threads, logs, nothing. They even dug into the kernel messages using DMESG and found the culprit. Tokyo runtime-W, the runtime for the async tasks, was the victim of the OOM killer. The DMESG output clearly showed the engine gateway process exceeding its memory limit.
But if the monitoring didn't show a problem, how could the memory usage have spiked so dramatically? Was it a sudden, massive request?
That's the million-dollar question. The monitoring frequency was 10 seconds, and the memory surge happened faster than that. The team initially doubled the memory limit, hoping to catch it in the act. But the problem persisted. Several weeks later, it happened again, this time taking down all instances of the service.
Yikes! A full-blown outage. So what was the next step? A deep dive into the code, I presume?
Precisely. They increased the memory limit to 4 gigabytes and switched to Gmalloc, a memory allocator that provides better profiling capabilities than the default libc allocator. They used the Rust Gmalloc-keep professor crate to generate flame graphs of memory allocations. This allowed them to pinpoint the source of the problem.
Smart move using Gmalloc. So did the flame graph immediately reveal the culprit?
Not quite. They had to wait a few days, but eventually they saw a memory increase of over 400 megabytes. The culprit? A seemingly innocuous line of code logging an error using error. Error while getting Git token?
Wait, just logging an error? That seems incredibly unlikely. What was so special about that line?
The key was the format specifier, which uses the debug implementation of the anyhow error type. This triggers the generation of a backtrace, which is quite memory intensive, and because anyhow captures a backtrace for every error, this seemingly small log statement was causing a massive memory allocation.
Ah, I see. The debug implementation was the hidden cost. So the solution was simply to change the logging format?
Not exactly. They realized that they only needed backtraces during panics, not for every error. The fix was to set the environment variable rustla_backtrace equals 0, disabling backtraces for library errors. No code changes were needed.
That's a fantastic example of how a seemingly minor detail can have huge consequences. It also highlights the importance of thorough monitoring and using the right tools for debugging. A great lesson learned.
Absolutely. This case study underscores the importance of understanding your tools, monitoring effectively, and being aware of potential pitfalls even in seemingly safe languages like Rust. And remember, folks, sometimes the simplest fix is the best one. Thanks for tuning in to Tech Bytes and News. Have a great day.
Bye-bye.